In today's lesson, we are going to talk about addition and subtraction of vectors. Let's say we have two vectors, u and v. The question is that how are you going to find the sum of the two vectors u plus v? We call the sum of the two vectors to be another vector, something like r, which is called the resultant. Now, to find the sum of two vectors, we can use three methods. Two of them are graphical methods, and the third one is algebraic method. The two graphical methods are very simple. The first one is the one we call head to tail method. The way we do it is very simple. Let's say we want to add u and v, which is given here. What we are going to do is that we are going to draw v at the end of vector u. So we are going to draw v here. You can see that the head of u is attached to the tail of v. When we add these two, the resultant is going to be a vector which is connecting the tail of u, which is here, to the head of v, which is there. This is called the resultant vector. The next method is called tail-to-tail method. The tail-to-tail method is saying that when you have to add two vectors u plus v, just connect the tail of two vectors together. To do this one, I'm going to draw the equivalent to vector v, which is going to be another vector parallel to v with the same magnitude. So it's going to be a vector looks like the following. Now I have two vectors with the tail attached. What I'm going to do now, I'm going to draw a parallelogram like the following. And the diagonal of this parallelogram is going to be the resultant, which is going to be like this. So this is called tail-to-tail method. So again, to repeat what we have covered so far, if we have to add two vectors, either we can attach the head of one to the tail of the other one, like this, and then connect the tail of the first one to the head of the second one. This is going to be resultant. Or attach the tail of both vectors, which is going to be something like this one. This is your v, and then make a parallelogram, and then you draw the diagonal, which is going to be the same resultant as we found before. The third method, which is much better than these two methods, is called components method. In the components method, every vector is going to be expressed as its components along the x and y coordinates. For instance, if you have your vector u or vector v is given, and we know the angle that it makes with the x-axis, and also we know the magnitude of the vector, then we can express vector v in terms of its components along x and y. Let's assume the component of the vector v along the x is v sub x, and the component of the vector v along the y is v sub y. So I can write that vector v is v sub x, which is the component along x, times a unit vector along x, which we denote with the vector I. So it's going to be v sub x times I. Again, I is a unit vector. This means that it's along the x direction, along the positive x direction, and also the magnitude is 1. Plus, let's assume that the component of v along the y direction is v sub y. So we will have v sub y times j. J is the unit vector that we use along the y-axis. Let's assume that vector u, the second vector, is going to have the same thing, u sub x I plus u sub y j. Now, when we are adding the two vectors, v plus u, the terms which are involved with the unit vector I are the like terms, so we can add them together. So this means that addition of vectors v and u is going to give us v sub x plus u sub x times the unit vector I plus v sub y plus u sub y times the unit vector j. This is going to give us the vector v plus u. If you want to find the magnitude of the sum, meaning v plus u, we are going to find the square root of v sub x plus u sub x squared plus v sub y plus u sub y squared, which is exactly like Pythagorean theorem. This is going to give us the magnitude, and if we want to find the angle between the vector v plus u with the x-axis, then we are going to use the prime trig ratio tan theta, which is v sub y plus u sub y over v sub x plus u sub x. And then we are going to find the inverse to find the actual angle that the vector makes with the x-axis. This method of the components probably is the easiest way to find the sum of the two vectors, which we are going to use it later on in the next 2 units. In the first example, let's say you walk north 800 meters and then west 600 meters. What is the resultant vector? We are going to do this question in 2 different ways. We are going to use the addition of the two vectors that we talked about tail to tail or head to tail, and also we use the component method. The first one, I'm going to draw these two vectors. So I'm going 800 meters north and then 600 meters west. The resultant vector, as you can see, it's already head to tail, so the resultant vector is going to be a vector like this one. This is going to be our resultant vector. Now, to find the magnitude of the vector, I can use Pythagorean theorem, and I can say that the magnitude of r is the square root of 600 squared plus 800 squared, which is going to be equal to 1000 meters. Now, to find the angle, which is this angle theta, we are going to use primary trig ratio, and we're going to say tan theta is opposite, which is 600, divided by adjacent, which is 800. From here, theta, if you use the inverse on your calculator, is going to be about 37 degrees. So I can say that R is equal to 1000 meters north 37 degrees west, if I want to use the quadrant rotation. If I want to use the true bearing notation, remember this is your north, and I have to look at this angle. So I can say also R can be written as 1000 meters, and the whole thing is 360, so it's going to be 360 minus 37, which is going to be equal to 323 degrees. So this is going to be 1000 meters, 323 degrees true bearing. Now let us solve the same problem using components method. We know that the first part of the journey is north 800 meters. So again, this is 800 meters going north, and then going west 600 meters, and we have to find the resultant. This vector I can represent it as vector v, and since it's going up along the y-axis, so this will be 800j. And remember, it's going up, so it's in the direction of positive y. The other vector, which we call it, let's say u, is going to be 600 meters, but it's going in the negative x direction, so it's going to be negative I. Now, the resultant v plus u, which is going to be r, the resultant vector, is going to be negative 600i plus 800j. Now, as I said before, the magnitude of the resultant is going to be square root of 600 squared, or negative 600 squared, which is going to be positive, plus 800 squared, which is going to be 1000 meters. And if we denote this angle to theta, we can say that tan theta is 600 divided by 800. Remember, we are not going to use negative 600 because we know that the angle theta is in the second quadrant, so we are going to divide the measure of length in front of it, which is 600, divided by adjacent, which is 800. If we find theta here, theta is going to be about 37 degrees. So the resultant again is going to be 1000 north 37 degrees west. Again, as you can see, using component method is much easier and straightforward. We are going to talk about parallel vectors now, that they have the same direction. Let's say u is this vector and v is another vector which is parallel to u, but not necessarily the same magnitude. If you want to find u plus v, we're just going to put the tail of one on top of the head of the other one. So this becomes, if we find the equivalent vector to v and then move it here, this is going to be v, and the resultant is going to be this vector, which is u plus v. The other case is when two vectors are parallel but in opposite direction, something like this one. And what we have to do is very simple. Again, we put the tail of one on the head of the other one. So if I find or draw the equivalent of v is going to be something like this one. So the sum is going to be this vector u plus v. Now, the magnitude is going to be the difference of the magnitude of these two vectors u and v, and the direction is going to be in the direction of the longer vector, which in this case is going to be u. The next case is, what about subtracting vectors? Meaning, if I have a vector like u here, and I want to subtract it from a vector v, which is drawn here, we can say that u minus v is the same as u plus negative v. Now, negative v means the same vector, the same magnitude, but in opposite direction. And then you're going to add them. So this means if u again is this one and v is this one, negative v is going to be this one, opposite direction. And now we know how to add two vectors using any one of those three methods that I mentioned before, meaning head to tail to tail, or component method. We can find the sum of these two vectors u and v, these two vectors. The next scenario is when you are adding two vectors which are of the same magnitude and in opposite direction. Let's say I have u looks like this one and v looks like this one. U and v the same magnitude but in opposite direction. Obviously, u plus v is going to give me a vector of magnitude 0. So this case, we are going to introduce a new vector called 0 vector, which doesn't have any magnitude and no direction. So when we are adding two vectors which are in opposite direction and have the same magnitude, we are going to get 0 vector. No magnitude, no direction. The next example, we have two vectors drawn here, and we are supposed to find the sum and the difference between the two vectors. To find the sum, let's say again, let's redraw v. This is v. To redraw u, I'm going to draw an equivalent vector. This is u. And the way that I have drawn it, I'm going to use tail-to-tail method. So this means that I can draw the parallelogram like this one, and the diagonal, which is this one, is going to be my resultant vector. You can also use the other method, which is head to tail, and you're going to get the same thing. The next one, we are going to find the difference between u and v. So we know the u is drawn here, but we have to draw the negative of v. The negative of v is going to be a vector which is parallel to v, but in opposite direction. So it's going to be this way. Now again, they are in tail-to-tail position. To find the resultant, we are going to form the parallelogram here, and then we are going to draw the diagonal. So the resultant is going to be this vector. In the next example, we have a parallelogram EFGH with diagonals EG and FH that intersect at point J. we're supposed to express the following vectors as the sum of two other vectors in two different ways. The first one is HF. The way I'm going to do it is that I look at the vector HF. I'm going to look at other vertices around H. These are E and G. J, I'm not going to use it because it's going to lie on the same vector HF. So I'm going to look at E and G. Then I'm going to use either one of these vertices within H and F, meaning if I put E in between H and F, I'm going to write HE plus EF. You can see HE plus EF gives you HF. Another one is using G. I'm going to write HG plus GF is going to give me again the vector HF. For FH, I'm going to look at FH. I can use E and G again. So I'm going to say FE plus EH is going to give me FH, and FG plus GH is going to give me the same thing, which is FH. For GJ, I'm going to use, for instance, vertex F. So I'm going to say GF plus FJ. GF, which is this one, plus FJ, which is this one. Obviously, it gives you GJ. I can also use vertex H. I can say GH plus HJ. GH plus HJ is going to give me GJ. The next one says express each vector as the difference of two other vectors in two ways. For the first one, HF, I look at the previous example and I see two ways of expressing as a sum. So if the second vector, I use the difference of the vectors, then in the first one I had HE plus EF. Now I can write HE minus FE. For the second one, I'm going to write HG minus FG. For the second question, which is FH, I know as the sum is FE plus EH. Now I'm going to write it as FE minus HE. Because remember, when I change it to minus, then the beginning and end of the vector, they flip. For the second one, I'm going to write FG minus HG. For the third one, I'm going to write GF minus JF and GH minus JH. In the next example, we have a race that you walk 100 meters due east. So you go 100 meters here. Let's call it U. And then you walk north 70 degrees east. So if I draw another coordinate system here, you go north and then 70 degrees east. So this is 70 degrees. And you go 60 meters. Let's call this one V. How far are you from starting position and at what bearing? Okay, to do this one, I'm going to represent each vector as a component. So I know that U is 100 I because it's going in toward the positive direction in X. And our v, we have to find the components. We can write v as 60 sine 70, because here this is your I component, so it's going to be sine 70 times 60i plus 60 cos 70j. So this is going to be my vector v. Now to add them up, I'm going to say v plus u, which is my r resultant, is going to be 100 plus 60 sine 70i plus 60 cos 70j. Now to find the magnitude of the resultant, I just find the square root of 100 plus 60 sine 70 squared plus 60 cos 70 squared. This is going to give me approximately 158 meters. So this means this vector, which is resultant, has a magnitude of 158 meters. And to find the bearing, I have to find this angle. This angle, you can see, is going to be tan theta is 60 cos 70, which is this one, divided by the I component, which is 100 plus 60 sine 70. This is going to give us approximately 7.5 degrees. Now, if I want to use the quadrant bearing, then I have to subtract 7.5 from 90, because in the quadrant bearing, remember, I need this angle, not this angle. So if I subtract 7.5 from 90, I get about 82.5 degrees. So the resultant vector is going to be 158 meters north, 82.5 degrees east. In the last example, we are going to find an expression after it's simplified. For instance, the first one is u plus v minus u. This is the same as u plus v minus u. U cancels with u, so we get v here. The next one is p plus q minus p minus q, which is the same as p plus q minus p minus q after we drop the square brackets and brackets. P cancels with negative p, q with negative q, so the answer is 0 vector.